Good morning everyone. In this particular video lecture we will discuss the next topic, that is series RLC circuit. Now my dear friends, in the previous video we discussed regarding the series RC circuit and series RL circuit, and in this particular video we will discuss the series resonance and series RLC circuit. Now my dear friends, as you can see here, this is basically the circuit diagram for the series RLC circuit. As you can see here, there are three elements connected in series. The first one is resistor, the second one is inductor, and the third one is basically capacitor. And there is a voltage source connected, that is VT, we can say V, and the current flowing through all these three elements is basically denoted by I. Now my dear friends, as you can also see here, that is the voltage across resistor is denoted by VR, the voltage across inductor is denoted by VL, and the voltage across capacitor is denoted by VC. Now my dear friends, as we move further, then as you can see here, we know that the voltage across basically first of all we will see the phasor diagram. As we know, as in case of resistor, the voltage and the current both are in same phase, and we can say the phasor angle is basically 0 degree. And my dear friends, in case of inductor, if we talk, then in case of inductor, then voltage, that is VL, basically leads to the current I by 90 degree, as you can see here. Now my dear friends, in case of capacitor, if we talk, then we can say that in case of capacitor, the current I basically leads to the voltage by 90 degree, as you can see here. Now my dear friends, as we know that the voltage across resistor is denoted by VR, and here we know that VR is equal to I into R, and also we know that there is a angle of basically 0 degree between the voltage and current in case of resistor. So here we have denoted it as I into R at angle 0 degree. Now my dear friends, if we talk regarding the voltage across inductor, that is VL, then as we know that the voltage in case of inductor basically leads the current by 90 degree, as you can see here. So here we are using basically plus 90 degree. And my dear friends, in case of capacitor, if we talk, then as we know, the voltage basically lags to the current with the angle 90 degree. So here we are using basically minus 90 degree, I into XC minus 90 degree. And now my dear friends, in the whole circuit, if you want to calculate the basically equivalent voltage, then that will be basically comes out to be, as you can see here, V is equal to voltage across resistor plus voltage across inductor plus voltage across capacitor, my dear friends. Now we will put all these value here, and the equation will be comes out to be, after taking I as common, the equation will be comes out to be V is equal to I into R plus JXC minus R plus JXL minus JXC. Now my dear friends, if we send this I to the LHS side, then that will be basically comes out to be V by I is equal to R plus, and from these both two we will basically take plus J as common. Then the equation will be basically comes out to be V by I is equal to R plus J into XL minus XC. Now my dear friends, as we know, V by I is basically equals to R, that is resistance, and in this case, that is in series RLC circuit, we will basically denote it by Z, that is impedance. Now my dear friends, as you can see here, Z is equal to basically R plus J XL minus XC, my dear friends. This is basically impedance. And now my dear friends, the value of XL minus XC, we will denote it by X net, we can say. X net will be equal to basically XL minus XC. So now my dear friends, as you can see here, basically this will be basically Z, and it is denoted by impedance, and it will basically equals to R plus J into X net, and its unit will be basically ohm. Now my dear friends, we will try to draw the phasor diagram in this case, that is in a series RLC circuit. For drawing phasor diagram, my dear friends, first of all we will discuss regarding the case 1. In case 1, my dear friends, as you can see here, we will basically take that the XL is greater than XC, or we can say VL is greater than VC, my dear friends. Now in this case, if we take XL is greater than XC or VL is greater than XC, then such type of phasor diagram will be available to you if we draw. Then here, as you can see that this is now my dear friends, in series circuit, as we know, we take I means current as a reference, and then as we know, in case of inductor, basically this will be what will be this will be basically VL means voltage across inductor, because as we know that the voltage across inductor will basically lead to the current by 90 degree. And my dear friends, this will be basically becomes VC means voltage across capacitor, because my dear friends, we also know that the voltage in case of capacitor basically lags to the current by 90 degree. Now my dear friends, here we have taken the case that VL is greater than VC. So my dear friends, this is basically VC and this is basically whole we can say VL. So my dear friends, if we project this VC to here, then that will basically comes out to be VL minus VC. This will be basically VL minus VC, my dear friends. And now my dear friends, as we know, the voltage and current basically in case of resistor are in same phase. So this is basically the current and the voltage across resistor will be in the same phase, my dear friends. So this is basically denoted by VR. Now my dear friends, as you can see here, this will from here to here, this is basically total VL, and if we project this from here to here, my dear friends, this is basically VC. So my dear friends, if we project VC on VL, then we will get from here to here that VL minus VC, my dear friends. Now my dear friends, we will basically try to find out the equivalent voltage, then that will basically V, my dear friends, as you can see here. So my dear friends, this is basically our equivalent voltage, and as you can see here, the equivalent voltage will basically we can say lead to our respective current by angle phi, which is basically we can say less than 90 degree, as you can see here in the phasor diagram. Now my dear friends, we will now proceed to our next calculation. That, my dear friends, as we know, V is equal to, we can say, VR plus J VL minus VC, my dear friends. If you want to calculate the value of magnitude of voltage from here, then as we know, root under means imaginary square of imaginary part, or plus we can say a square of real part. So this is basically the imaginary part and this is basically the real part. So the magnitude of V will be VR square plus VL minus VC square. Now my dear friends, in this basically phasor diagram, if you want to calculate the value of tan phi, then that will basically comes out to be VL minus VC by VR. And if you want to calculate the value of phi, then that will basically comes out to be phi is equal to tan inverse VL minus VC by R, my dear friends. Now we will basically calculate the value of cos phi from here. If you want to calculate the value of cos phi, then that will be basically comes out to be VR, as you can see here, VR by V. So now my dear friends, as you can see here, the value of cos phi is equal to VR by V, VR by V. And now my dear friends, from the phasor diagram, as we know, the voltage is basically leading to the current by angle phi, which is less than 90 degree, and this case is basically, or we can say, the current is lagging behind. So here we can say, my dear friends, that this is basically the circuit is lagging in nature. Now my dear friends, if you want to calculate the value of sin phi from the same phasor diagram, then that will basically comes out to be, we can say, VL minus VC by V. Now my dear friends, we will consider the second case, that is if XC is greater than XL, or we can say VC is greater than VL. Now my dear friends, if we will consider this case, then our phasor diagram will comes out to be something like this, as you can see here. So my dear friends, in this figure, if we see, then as you can see here, this is basically our VL and this is basically our VC, and this part is basically our VL minus VC, my dear friends. Now my dear friends, this is VR and this is our equivalent voltage. So my dear friends, in this case, if we talk, then our equivalent voltage is basically we can say lagging to our respective current by angle phi, which is less than 90 degree, as you can see here in the phasor diagram. Now my dear friends, in this case, we also know that the value of equivalent voltage will be VR minus J into VC minus VL, my dear friends. Now my dear friends, if you want to calculate the value of equivalent voltage, then that will be basically comes out to be root under VR ka square plus VC minus VL ka whole square. Now my dear friends, if you want to calculate the value of tan phi from here, then that will basically comes out to be VC minus VL by VR. And now my dear friends, in the same way, if you want to calculate the value of phi from here, then that will basically comes out to be tan inverse VC minus VL by VR, my dear friends. Now my dear friends, if you want to calculate the value of cos phi from the same triangle, then cos phi will be VR by V, as you can see here. And now my dear friends, from the phasor diagram, as you can see here, the current is basically leading to the voltage. So we can say that this circuit is overall leading in nature. Now my dear friends, as you can see here, if you want to calculate the value of power factor, then power factor will be equal to cos phi, and from the triangle, cos phi will be equal to VR minus VR by V, as you can say. Now my dear friends, if you want to calculate the value of sin phi, then that will basically comes out to be VC minus VL by V, my dear friends. And from here, that is power factor, if you want to calculate the value of VR, then it will basically comes out to be VR is equal to V into cos phi, my dear friends. Now the next case will be, my dear friends, when XL is equal to XC, or we can say VL is equal to VC, as you can see here. Now my dear friends, if you in this case, as you can see here the value of VL is equal to VC. And as you can see here, so if you want to draw the equivalent voltage, then that will basically comes out to be this will basically comes out to be V. And my dear friends, as you can see here from the diagram, that V is equal to, we can say, VR. That is, my dear friends, the circuit is resistive in nature, or we can say that the equivalent voltage in the case when VL is equal to VC is basically in phase with the current. So my dear friends, in this case we can say that our circuit is resistive in nature, my dear friends. Now as you can see here, the from the phasor diagram, in case third, that V is equal to VR, means the overall voltage is equal to the resistive voltage, my dear friends. And the value of angle, that is phi, is equal to 0 degree, because as you can see here in this diagram, this is basically the reference current I, and this is basically in the same phase our overall voltage V is basically lying. So we can say that the phasor angle is basically 0 degree. Now my dear friends, as you can see here, as you can see here from the diagram, that this diagram is basically resistive in nature. So we can say that if you want to calculate the value of cos phi, that is we can say cos phi, that is power factor, then that will basically cos 0, and it will basically comes out to be 1, that is unity power factor, or we can say UPF in short. Now my dear friends, after drawing complete phasor diagram, as you have seen that basically in case of series RLC circuit, there are 3 cases for drawing, we can say, phasor diagram. In the same way, if you want to draw the impedance triangle in case of series RLC circuit, then there will be basically, my dear friends, 3 cases. If now we will basically discuss all the case one by one. In case of, my dear friends, impedance triangle, as you can see here, this is case 1. In case 1, as you can see here, XL is greater than XC, my dear friends. Now if you in the same way, my dear friends, in the previous, in the phasor diagram, you have drawn that this is basically our current I, and this was basically our voltage VL, and this was basically our, my dear friends, VC, and this was basically our, my dear friends, VR. Now my dear friends, from here VR is equal to I into R, so we will take resistor R at the horizontal axis. Now my dear friends, here there is VC, my dear friends, here now my dear friends, as you can see here, in the phasor diagram, this was basically VL, and if you want to calculate the VL, then that will be basically plus Ji into, my dear friends, XL. So my dear friends, from here we will take XL, or we can say here we have denoted it by XL. Now my dear friends, if you want to calculate as you can see here, below, my dear friends, below, as you can see here, there is VC, there is XC, and in phasor diagram this was basically VC, and we know that VC is equal to minus Ji into, my dear friends, XL. So my dear friends, from here we have taken XL and it denoted it by XL. So my dear friends, now the case was basically XL is greater than XC, means this part is basically greater than this one. So my dear friends, if you want to project this part of XC on XL, then that will basically comes out to be, this will basically comes out to be XL minus XC, my dear friends. Now this is basically R, and if you, and this is our XL minus XC. So if you want to draw the equivalent impedance, then that will basically comes out to be Z, and this one will basically comes out to be Z. Now my dear friends, as we know, in case of series RLC circuit, the equivalent we can say impedance, that is Z, will be equal to R plus J XL minus XC, my dear friends. So my dear friends, as you can see here, Z is equal to R plus J XL minus XC, my dear friends. Now if you want to calculate the value of magnitude of Z, then that will basically comes out to be root under R square plus XL minus XC whole square, my dear friends. Now my dear friends, from the same triangle, if you want to calculate the value of tan phi, then that will basically comes out to be XL minus XC by R. And if you want to calculate the value of resistance from here, or we can say from the value of phi from here, then that will basically comes out to be phi is equal to tan inverse XL minus XC by R, as you can see here. Now the next calculation we will do is to calculate cos phi, that is power factor. If you want to calculate the value of cos phi from here, then that will basically comes out to be, as you can see here, r by z, that is we can say base by hypotenuse. Here in this case, base is basically resistance and hypotenuse is basically our z. So my dear friends, in this case power factor will be equal to r by z. My dear friends, we will discuss the next case, that is leading case. In this case, my dear friends, as you can see here, the value of xc will be greater than xl, my dear friends. So my dear friends, if we will draw the impedance triangle in this case, then that will basically comes out to be something like this. And now my dear friends, this is basically the xc minus xl part, and this is resistive part. And now my dear friends, this is basically the equivalent impedance z. Now my dear friends, as you can see here, the value of z means impedance is equal to r minus j xc minus xl. And now my dear friends, if you want to calculate the magnitude of z, then it will basically comes out to be root under r square plus xc minus xl ka whole square. Now my dear friends, if you want to calculate the value of tan phi from here, then that will basically comes out to be xc minus xl by r, my dear friends. And now my dear friends, the value of phi from here, if you want to calculate the value of phi from here, then that will basically comes out to be, as you can see here, tan inverse xc minus xl by r. And in the same way, my dear friends, if you want to calculate the value of power factor, that is cos phi from this triangle, then that will basically comes out to be r by z, as you can see here. Now the next case, that is third case, will be if xl is equal to xc, my dear friends. If the value of xl and xc will be equal, then the value of we can say the equivalent impedance will be along this, and that will be equal to basically r, means resistive circuit. So as you can see here, the value of z will be equal to r, and in this case the circuit will be resistive, that is the value of angle between the voltage and current will be 0, that is phi is equal to 0. So in this case, again, if you want to calculate the value of power factor, that is cos phi, then that will basically comes out to be 1, that is unity power factor, my dear friends. Now, my dear friends, we'll now move to the next topic, that is we will now draw the power triangle in this case. Now my dear friends, as we know that the value of voltage in case of series RLC circuit is equal to V is equal to VR plus J VC VL minus VC, my dear friends. Now as we know, the value of power is equal to V into I, or we can say I square R, my dear friends. Now my dear friends, in this equation, if we multiply by I both the case on both the side, then that will basically comes out to be Vi is equal to VR into I plus I into Ij VL minus VC, my dear friends, as you can see here. So here we have denoted V into I by S, or we can say as a and now my dear friends, we can say that the here we have represented VR into I with P, and we can say I into VL minus VC as now my dear friends, first of all, for understanding this case, we have to understand a thing that here if we will break, then the something equation will be like this, as you can see here, I J VL and minus I J VC. Now my dear friends, from this equation here, we can write it as if we take J as a common. Now my dear friends, if we take J as common, then wait, let me to, if we take J as common, then that will basically comes out to be I and again VL, my dear friends, and then minus I into, my dear friends, VC. And now my dear friends, here I into VL is denoted by QL and I into VC is denoted by QC, and J is taken as common, my dear friends. Now my dear friends, if we proceed further, then if you want to calculate the value of S from here, then as you can see here, that will basically comes out to be, as you can see here, S is equal to root under P square plus QL minus QC ka whole square. Now my dear friends, as you can see here, this is basically the what we can say power triangle in case where now my dear friends, as we know that here in case in phasor diagram we draw VL, and here we draw, my dear friends, VC. Now my dear friends, here is showing that QL is greater than QC, QL minus QC means QL is greater than QC, so it is obvious that the VL VL will be greater than VC, my dear friends. So here we have drawn that QL is greater QL minus QC to the above the horizontal axis. Now my dear friends, from this triangle, if you want to calculate the value of tan phi, then as you can see, a tan phi will be basically equals to QL minus QC by P. And in the same way, if you want to calculate the value of phi, then that will basically equals to tan inverse QL minus QC by P. And in the same way, my dear friends, if you want to calculate the value of power factor, that is cos phi, then as you can see, your cos phi is equal to base, that is P, and hypotenuse, that is S. And from here, if you want to calculate the value of P, then that will basically comes out to be P is equal to S cos phi. And we also know that S is equal to basically V into I, so we can say that basically P is equal to V into I cos phi. And one more important point here to be remembered is that V and I should be in RMS. Now my dear friends, we will basically move to the next topic, that is series resonance. My dear friends, this is basically the last topic of unit 1, AC series circuit. Now my dear friends, in series resonance circuit, first of all we will discuss regarding the circuit of series resonance circuit. My dear friends, as you can see here in this series resonance circuit, my dear friends, let me revise a little bit what we have discussed previously. As you can see here, my dear friends, we have basically discussed regarding the, as you can see here, a series RLC circuit. And then we have drawn, my dear friends, the phasor diagram. As you can see here, the phasor diagram containing both the case 1 is basically XL is greater than XC, case 2 is basically as you can see here, XL is less than XC, and case 3 is basically XL, we can say, is equal to XC, my dear friends. And in the same way, my dear friends, we discussed the next topic, that is impedance triangle, and then further we discussed the power triangle. And now we will, my dear friend, basically discuss the series resonance. Now my dear friends, this is basically the circuit of series resonance. As you can see here, basically this is there are 3 elements connected in series. The first one is resistor, the second one is inductor, and the third one is capacitor. Now my dear friends, we have denoted here the value of voltage across a resistor as VR, the value of voltage across inductor is VL, and the value of voltage across capacitor is VC, my dear friends. Now my dear friends, the overall current in the circuit is denoted by basically I, and this is basically the overall voltage source, we can say. Now my dear friends, as we know, the value of voltage is equal to I into Z, that is I means current and Z means impedance, or we can say resistance. Now my dear friends, as you can see here, V by I will be equal to Z, and in case of series RLC circuit, we have shown that the value of Z will be equal to R plus J XL minus XC. My dear friends, one point to be noted here is that this circuit is totally same to the series RLC circuit, which we have discussed just earlier. Now my dear friends, the value of impedance here will be equal to the same as that of series RLC circuit, and that will be equal to R plus J XL minus XC. Now my dear friends, here as you can see here, we also know that I is equal to V by R, or V by Z, we can say impedance, and here we have put the value of the Z, that is basically this is basically the value of current. Now my dear friends, as you can see here, the frequency at which the net reactance, we can say reactance means, my dear friends, basically XL minus XC, my dear friends. As we know, there are basically there are two type of reactance. Reactance is basically denoted by X. There are two type of reactance. The first one is inductive resistance, inductive reactance, which is denoted by XL, and the second one is basically capacitive reactance, which is denoted by, my dear friends, XC. So the net reactance will be XL minus XC, my dear friends. So my dear friends, as you can see here, this is basically as you can see here, the frequency at which the net reactance of series circuit is 0 is called the resonance frequency. Now my dear friends, in the topic resonance, series resonance, we will first of all we will discuss the resonance frequency. Basically, as you can see here, resonance frequency is denoted by F naught, or we can say omega naught, and its definition is basically the frequency at which the net reactance, that is XL minus XC, is 0 is basically the resonance frequency. Now my dear friends, as you can see here, as we equate XL minus XC to 0, then that will basically comes out to be XL is equal to XC. And now my dear friends, as we know that XL is equal to omega into L, as you can see here, and we also know that XC is equal to 1 by omega C. Now my dear friends, if we proceed further in calculation, then omega square will becomes out to be 1 by LC. And if you want to calculate the value of omega, then that omega naught, then that will basically comes out to be 1 by root under LC, and its unit will be radian per second. My dear friends, we also know that omega naught is equal to 2 pi f naught, where f naught is basically the resonance frequency, my dear friends. So my dear friends, from here, if you want to calculate the value of f naught, then that will basically comes out to be 1 by 2 pi root under LC. My dear friends, this formula is very important from an objective point of view. So this formula should must be remembered. And it's my dear friends, this is basically frequency, so its unit will be hertz. Now my dear friends, from the above equation, this is basically the equation of current, as you can see here. This is basically the equation of current, as you can see here. And in case of my dear friends, series resonance, the value this value will be total equal to 0. If we equate this value to 0, then as you can see here, this equation will becomes out to be, as you can see here, if we equate the value of net reactance, that is XL minus XC is equal to 0, then the value of current will becomes out to be V by R, my dear friends. Now my dear friends, as you can see here, the current at resonance is denoted by I naught, and its value will be V by R. So my dear friends, as you can see here, there is no any, we can say, reactive or we can say there is no any capacitive or we can say inductive term here. So we can say that the circuit at series resonance will be pure resistive circuit. So we also know that in case of pure resistive circuit, the angle between the voltage and current is 0. So here, if you want to calculate the value of power factor, then that will basically comes out to be unity power factor, that is 1, my dear friends. Now we will discuss the phasor diagram. Now my dear friends, as we know, the net reactance, we can say, means XL minus XC in case of series resonance is equal to 0. So my dear friends, from here we can calculate that XL will be completely equals to XC. And according to this, if you want to draw the phasor diagram, then my dear friends, as you can see here, this will basically your phasor diagram. This will basically your phasor diagram. And if you want to draw the impedance triangle, then my dear friends, this will basically our impedance triangle. So my dear friends, from this triangle also we can conclude that in case of series resonance, our circuit will be purely resistive, and our we can say the power factor will basically comes out to be unity power factor, that is 1. Now my dear friends, there are something most important point regarding the series, we can say resonance. As you can see here, when an RLC circuit is in resonance, the net reactance, as we have already discussed, will be equal to 0, as you can see here. And my dear friends, as you can see here, circuit impedance is minimum. In case of series resonance, the circuit impedance will be minimum, and that will be equal to R, my dear friends. So the circuit admittance is maximum, we can say. If the value of impedance means Z will be minimum, then as we know, basically 1 by Z is basically admittance. So my dear friends, admittance will be maximum. And now my dear friends, the next point is that circuit current is maximum, because my dear friends, impedance is basically minimum. So my dear friends, as we know, if resistance or impedance is minimum, so my dear friend, current will be maximum, as you can see here, and it will basically equals to V by R, my dear friends. Now we will discuss the fourth point, that is power dissipation, my dear friends. As we know, power dissipation is equal to I square R. So my dear friends, as you can see here, this is basically I square R, power dissipation. And my dear friends, if we talk regarding the power factor angle, then in case of series resonance, the angle between the voltage and current is 0, that is circuit is purely resistive in nature. So the value of cos phi, that is power factor, will be equal to 1, my dear friends. Now my dear friends, as you can see here, the value, this is also the, my dear friends, this is also the value of power, we can say, or I square R, V square by R, or we can as you can see here. Now my dear friends, in case of series resonance, we can say VL minus VL minus VC is also equals to 0, because as we know, the XL minus XC value, XL minus XC is equal to 0. So from here, if we common I, then VL minus VC will be equal to 0. So we can say that the voltage across inductive and the voltage across capacitor both will be equal, my dear friends, as you can see here. Now we also know that we have derived that this is basically the resonance frequency, my dear friends, and resonance frequency will be 1 by 2 pi root 100 LC, my dear friends. Now my dear friends, we will discuss some important graphs. As you can see here, this is basically the graph between, we can say the reactance, that is X versus F, means frequency. Now my dear friends, as you can see here, as we know, there are two types of reactance. The first one is inductive reactance and the second one is capacitive reactance. And my dear friends, according to the formula, we know that XL is equal to J2 pi FL. From here we can say that XL is directly proportional to frequency, and from here we can say that XC is inversely proportional to frequency, my dear friends. So using this relation, XL is directly proportional to F and XC is directly proportional to 1 by F, we will draw a relation. As you can see here, this is the most important graph, my dear friends, and one point to be noted is that this graph is only for an understanding purpose. The correct this is basically our correct diagram. So in exam only we have to draw this diagram, and basically, my dear friends, this diagram is for understanding purpose. This diagram is for understanding purpose, my dear friends. We should not have to draw in exam. Only we have to understand by using the diagram, and this will basically our correct diagram. We have to only draw this in exam. So my dear friends, as you can see here, basically my dear friends, as we know that this is basically, we can say this graph is basically between the frequency is on the horizontal axis, as you can see here, and my dear friends, the reactance is on the vertical axis, my dear friends. Now my dear friends, as you know that XL is directly proportional to F, so its graph will be a straight line passing through the origin, and this will basically the XL. And my dear friends, as you can see here, the XC is directly proportional to 1 by F, means it is inversely proportional to frequency, so its graph will be of parabolic shape, as you can see here. Now my dear friends, from the intersection point, if we draw a point to cut on the horizontal axis, then this point will be basically our resonance frequency. As you can see here, this point will be our resonance frequency, my dear friends, which is denoted by F naught, F naught. Now my dear friends, this is basically our F naught, and on the left hand side of this, we will say it as a below F naught, and my dear friends, on the right hand side, we will denote it by above F naught. So my dear friends, as you can see here, below F naught region, the value of XC is greater than XL, my dear friends. So in this case, the circuit will be totally capacitive in nature, or we can say leading in nature. And above F naught, we can say the value of XL is greater than XC, my dear friends. So above F naught, we can say the circuit will be inductive in nature, or we can say lagging in nature. So my dear friends, this is basically the diagram to understand things. Now the main diagram is this one. Main diagram is this one, my dear friends. We have to only draw this diagram in exam. That was only for this was, my dear friends, this diagram was only for understanding purpose, my dear friend. So we don't have to draw in exam. Now my dear friends, let's discuss regarding the correct diagram. My dear friends, as you can see here, this is basically our we can say, my dear friends, XL, and this is basically, my dear friends, our XC, as you can see here. Now this is basically the point of intersection, my dear friends. If we draw the equivalent of both these two, so my dear friends, this will basically our F naught. And my dear friends, as you can see here, below F naught, we can as we know, below F naught, the XC is greater than XL. So below F naught, my dear friends, the circuit will be leading in nature, and above F naught, we can say the circuit will be lagging in nature, because in this case XL will be greater than XC, my dear friends. So this is basically the correct diagram between, we can say, the reactance and frequency. Now my dear friends, we will now discuss the next graph, that is IZ versus frequency. I means current, Z means impedance, and F means frequency, my dear friends. Now my dear friends, on the y-axis we will basically denote the I and Z, we can say, and on the x-axis we will basically denote, my dear friends, frequency. As you can see here, this is the graph of current, and this is the graph of impedance, my dear friends. And my dear friends, the point of intersection is denoted by A, and here is B. And now, my dear friends, if we project these both intersection on the frequency axis, then that will basically comes out to be f1 and f2. And now, my dear friends, this will be basically our f0. As you can see here, we called f2 as a corner frequency or upper cutoff frequency, or f1 as a lower cutoff frequency, or we can say corner frequency. Now, my dear friends, at this point, that is A and B, the value of current will be I naught by root 2. And at this point, my dear friends, the value of current, that is I naught, will be B by R, as you can see here. Now, my dear friends, here our main motive is to calculate the bandwidth. My dear friends, bandwidth is basically change in frequency, that is f2 minus f1, we can say. The upper frequency is f2 and the lower cutoff frequency is f1. So the bandwidth will be the difference of both this frequency, that is f2 minus f1. And if you want to also, we can say the delta f or delta omega is equal to omega 2 minus omega 1. And f1 and f2 are basically, my dear friends, corner frequency, as you can see here. Now, my dear friends, if you want to calculate the value of power at resonance, then that will basically comes out to be I square R, or we can say V square by R. And now, my dear friends, if you want to calculate the power at these 2 points, that is cutoff point, or we can say corner point, as you can see here, my dear friends, this is basically the point A and B. This is point A and this is point B. Now we will now, my dear friends, we will basically want to calculate the power at that these 2 points. Then that will basically comes out to be I square R. And my dear friends, from the graph we have seen that the value of current at that point A and B is I naught by root 2. So here, my dear friends, here, my dear friends, will basically put the value, and the equation will comes out to be half I naught square R. So, my dear friends, from here we can say that P1 is equal to P2 is equal to half power at resonance, means the power at point A and B will be equal to the half of the power at these 2 points. So, my dear friends, as you can see here, this is basically we can say the calculation of power at point A and B. Now, my dear friends, we will discuss the next concept, that is quality factor. Quality factor, my dear friends, as you can see here, quality factor is equal to VL by V, means voltage across inductor by V, or we can say that voltage across capacitor by V. So now, my dear friends, as you can see here, the quality factor we can also calculate by I naught by XL, by I naught by, we can say, the voltage. This is basically the value of, we can say, voltage across inductor by voltage across resistor. And my dear friends, this will basically comes out to be minus, we can say, this will basically comes out to be omega L by R, my dear friends. Now, my dear friends, for capacitor, if you want to calculate the value of we can say the quality factor, then it will basically comes out to be VC by V, or here if you put the value, then that will basically comes out to be XC by R, my dear friends. Now, my dear friends, this was all regarding the calculation of, we can say, quality factor. Now, my dear friends, this as you can see here, this was all the derivations of quality factor, my dear friends. Now we will move to the next thing, that is my dear friends, there is also this is the most important formula for the calculation of quality factor. Now, my dear friends, as you can see here, first of all, we will derive a relationship between quality factor, bandwidth, and we can say resonance frequency. As you can see here, quality factor is equal to this is resonance frequency and this is bandwidth, and we can also say that bandwidth is equal to R by L. And my dear friends, now we will discuss some very important point, that is, as you can see here, in series resonance circuit, quality factor is defined as the ratio of voltage across the inductor or capacitor to the applied voltage, my dear friends. This is basically, as you can see here, the voltage across inductor by applied voltage and voltage across capacitor by applied voltage, my dear friends. It is also the voltage magnification in the at resonance, my dear friends. This is the most important point, voltage magnification. In series resonance, there is a magnification of voltage, as you can see here, my dear friends. Now, my dear friends, as you can see here, this is basically the voltage magnification, as you can see here. And as you can see here, this is the voltage across inductor, voltage across capacitor, and this is the basically supply voltage. Now, my dear friends, we also derived that the power at we can say the point 1 and 2 is basically half the power at resonance, my dear friends. Now, my dear friends, that is why, as you can see here, this is why the 2 point A and B on the resonance curve is known as half power point, my dear friends, and the corresponding value of bandwidth is basically known as the half power bandwidth, which is basically, my dear friends, denoted by BHP, means half point bandwidth, half power bandwidth, my dear friends. Now the next thing we will discuss some more important point, that is, as you can see here, it is also called 3D bandwidth, my dear friends. 3D bandwidth, my dear friends. Now, my dear friends, there are some important points regarding point A and B, means current and point A and B. My dear friends, as you can see here, point A and B. Point A and B is basically this one. As you can see here from this diagram, this is point A and this is point B, about which we are talking. As you can see here, the current at point A and B will be I naught by root 2, and the value of, my dear friends, impedance will be root 2 into R, or we can say root 2 into Z. And if you want to calculate the value of power, then it will basically comes out to be P naught by 2, means power at resonance by root 2 by 2. And if you want to calculate the value of phase angle, then that will basically comes out to be plus minus, my dear 45 degree at point A and B, at point A and B, my dear friends. Now, my dear friends, we will basically discuss on numerical based on this concept. As you can see here, a 60 hertz voltage of 230 volt effective value is impressed on an inductance of 0.265 Henry. Write the time equation for the voltage and resulting current. Let the zero axis of the voltage wave be at t is equal to 0. Okay, so the voltage and current on a phasor diagram, and the third one is basically find the maximum energy stored in the inductor. Now, my dear friend, first of all, we will draw basically a circuit. As you can see here, a circuit is given where this is basically the inductor, this is our supply source, and this is the value of current. Now, my dear friends, in the question it is given that the value of L is 0.265 Henry. The value of Vrms is basically given to 30 volt, and the frequency is my given, and frequency is also given, my dear friends. Now, my dear friends, first of all, what we have to calculate is write the time equation for the voltage and resulting current. First of all, we have to write the time equation for voltage and current. Now, my dear friends, as you can see here, this is basically the time equation for, we can say, voltage, and this is basically the time equation for current, my dear friends. So, my dear friends, here first of all we will calculate the value of Vmax, or we know that Vmax is equal to Vrms into root 2, and from here we will calculate Vmax, my dear friends. And now, my dear friends, we will calculate the value of omega, that is 2 pi f, and after calculating all these value, we will put all these value into these two equation, and we will get the, we can say, the time equation for voltage and current, my dear friends. As you can see here, we have calculated first of all XL, and then we have calculated I maximum. I maximum will be basically, my dear friends, Vm by XL, and that will basically comes out to be 3.25 ampere, my dear friends. And now, my dear friends, XL is equal to, as we know, omega L, and omega is equal to 2 pi f into L, and we have put all this value here, and the value of XL is comes out to be 99.852 ohm. Now, my dear friends, as we put all these value in equation 1 and 2, then the value of time equation for voltage will be comes out to be 230 root 2 sine 376.8 t. And in the same way, my dear friends, the value of IT will be Imax. The value of Imax will be 3.25, and sine omega t, the value of omega is basically 376.8 into 2 minus pi by 2. And now, my dear friends, we have taken minus common, and then we can say 90 minus, we can say this is theta, and 90 minus theta is basically, we can say, cos theta, my dear friends. So the value of IT will be basically equals to minus 3.25 cos 376.80, my dear friends. Now, the next calculation we have to do is to, my dear friends, as you can see here, show the voltage and current on the phasor diagram. We have to basically show it on the phasor diagram, my dear friends. As we know, basically in case of inductor, my dear friends, the voltage is basically leads the current by 90 degree. So this is, my dear friend, current, and this is, my dear friend, voltage. And as you can see here, the voltage is basically leading the current by, my dear friends, 90 degree. So, my dear friends, we will move to the next thing, that is find the power, find the maximum energy stored in the inductor. We will, my dear friend, calculate the maximum energy, or we can say energy is equal to half L into I max k square. And as we put all these value, then the value of power will basically comes out to be 1.4 joule approx. Now, my dear friends, this was all regarding the series resonance and series RLC circuit. Now, my dear friends, we have successfully completed unit 1 from here, and from the next video we will start unit 2, that is, we can say, the parallel circuit, AC parallel circuit, my dear friends. Now, my dear friends, this was all regarding the AC3 circuit. I hope you have enjoyed this video. That's all. Thank you.